we've introduced the four thermodynamic processes and some formulas associated with them, including the adiabatic process, which we defined as the process that involves no heat exchanged with the environment. And this formula includes this gamma symbol in here. So this is the Greek letter gamma. It's lowercase gamma, and it looks kind of like that. I don't always draw it perfectly. If you want to see a better version, check out some of the ones on the slide here. They look a little bit better in terms of what they're supposed to look like. The definition of gamma is the ratio of the constant pressure heat capacity to the constant volume heat capacity of the system that you're looking at. And so when you see gamma in all these formulas, that's actually where it comes from. Now, I'm not going to connect all the mathematical dots for like how do you get to say this work formula from basic concepts. Even this statement that I've started here on the key concepts page, that is kind of a starting point for adiabatic processes, that pressure times volume raised to the power of gamma should be equal to a constant. That's something you could also write as saying that if I interpret pressure times volume raised to the gamma, if this is final pressure and this is final volume, since it's constant, those would be equal to whatever initial pressure the system started at times whatever initial volume the system started at raised to the gamma that describes that system. That's going to be a useful formula when you want to look at things involving adiabatic processes. So there's that formula and there's this formula, but there's also this definition, which is kind of formal, and you might say, oh, I don't want to do stuff with that. And that's good, because all you have to know really in most situations is whether you're looking at a monatomic gas or a diatomic gas, because it turns out for a monatomic gas, gamma is simply equal to 5/3. For a diatomic gas, it's maybe not always quite as close. In fact, both of these are kind of approximations. It turns out the equipartition theorem and kinetic theory of gases predicts these fractional values exactly. But if you go and say, well, what are the actual measured values and how close are they to this? For monatomic gases, it tends to be really close. For diatomic, it's close, but maybe not quite as close as monatomic gases. But for this class, we're going to find it perfectly acceptable to just remember it's either 5/3 or 7/5. And you might remember that earlier when it came to heat capacity, we saw that the constant volume heat capacity for monatomic involved like a 3/2 NR. Diatomic was 5/2 NR. And it turns out if you simply add 2 to that number that's in the numerator of that kind of fraction in those formulas, that turns out to be the correct number to use, as divided by 2, that is, for the constant pressure heat capacity, which simplifies when you take the ratio of those two to these really simple fractions. Another way of looking at it is it's the degrees of freedom plus 2 divided by the degrees of freedom for a single molecule. Remember, for monatomic, that's 3 degrees of freedom because it's moving in 3 dimensions. For diatomic, it's 5 degrees of freedom because it's 3-dimensional motion plus 2 internal rotations. And so when you add 2 to that number 5, you get 7, and then divide by the same number gives you 7/5. So again, if you just know those numbers, you'll be able to do what you need to do. And so then between that and this formula right here really is a thing to know, and then the one that we already have in our chart, those are the two things that we'd really like to know for this topic.